Welcome to the course on interfacial engineering. Okay, so in this lecture, being a first lecture, we would like to give you, module-wise contents details, and then we'll highlight some of the reference books that we will be following for this course. Okay, and then I'll show some of the examples using the from the day-to-day life, whatever we often see, and using those examples, I'll try to motivate you, in this lecture, and so then we will try to, cover the rest of the topics as we move on. Okay, so first let's start with the module-wise contents. Okay, so the module one will be mainly dealing with introduction to interfaces. Okay, and we'll try to emphasize on importance of surface. Okay, so coming from right from the macro objects and to the nano objects, nano-sized objects, how surface plays a vital role. Okay, so those aspects we will try to cover in the module one. We'll try to give you enough examples, applications, so that we can motivate you further on this topic. And the module two is all about the capillarity and surface tension. We'll first start with the basic concept of capillarity and surface tension. We'll try to understand more about the surface tension and three-phase contact angle. Three-phase contact angle and surface tension both go together simultaneously. So we will also talk about various techniques that measure the three-phase contact angle if surface tension is known, or surface tension if three-phase contact angle is known. And after that, we will also look at some of the popular equations often that we deal with in this topic. For example, Young-Dupré equation. Okay. And its application, Laplace equation. Again, the application of Laplace equation is what known as Kelvin equation. So those aspects we will try to cover in the module 2. Then we'll move on to module 3. In module 3, we will mainly look at surfactants and micelles. Okay. We also call micelles as association colloids. Because micelles are nothing but aggregation of surfactants. As they self-assemble to form micelles, they generally exist. The size varies between, let's say, few nanometer to, a few tens of nanometer up to 100 nanometer. So such aggregate structure, structure is also called as association colloids, right? So we'll mainly deal with surfactants and micelles, and we'll start with the introduction, and then we'll try to give enough insight into what is known as surface excess quantities. Okay, there is something called a positive surface excess, negative surface excess, right? And what are their consequences? We'll see them. And after that, we move on to Gibbs absorption isotherm equation, very famous equation. This gives you the relationship between the chemical potential and surface tension. We'll look at that after the surface excess quantities. Then we'll slowly move on to the tendency of surfactant. Okay, absorb that goes in absorbing the interfaces. Then that brings an important topic called CMC, which is critical micellar concentration. So we will understand how one can measure CMC for various surfactants. Okay. We'll also discuss various techniques that you can use to identify or to measure the CMC. After that, we'll try to cover up what is known as microemulsions. Okay. Micro nanoemulsions are emerging topics within this interfacial engineering domain. The last but not least is the liquid-solid interfaces. Here we'll start with colloidal dispersions. Okay, basic concepts behind colloidal dispersions. Then the properties of colloidal dispersions. Okay, how by tuning the properties of colloidal particle you can even change the quality of dispersions. Emulsion stability criteria and those aspects. After that, we will also look at different types of forces. For example, what is known as Van der Waals force, DLVO force, and electrical double layer interaction and all that. The last but not least in this model is electrokinetic phenomena. In this chapter topic, we will also provide enough insight into what is known as zeta potential. Okay, how it is different from surface potential, and what we can, what technique can be used to understand the zeta potential of any given, colloidal system when you disperse them into any known, medium, usually aqueous medium. Okay, and we'll also look at various models that are available to describe the distribution of the potential as a function of the distance from the object. Okay, and with this, I think we will complete important aspects of interfacial engineering, starting from module 1 up to module 4. Now, I would like to discuss about the various reference materials that are available. For example, Jeffrey Barnes and Ian Gentle. This is a textbook on interfacial science itself, and this book contains almost all the modules or topics that we discuss throughout this course. So it can be used as a textbook. And then we will also look at what is one can refer Hemans and Raj Rajagopalan book. The title of the book is Principles of Colloid and Surface Chemistry. Okay. Then comes Jacob N. and Israelishvili, Intermolecular and Surface Forces, right? And this is very important book when you want to understand the fundamentals of intermolecular and surface forces. Very popular book, and it provides all required fundamentals behind the intermolecular and surface forces. The last but not least is the book authored by Jim Goodwin, and this book is entirely, especially for if you want to understand surfactants, polymers, little more in detail, and colloids, little more in detail. You can always refer to this book. Okay, so these 4 books are can be referred to as we cover these as we move along with this course, right? So next I would like to give you a short introduction. First, let's understand what is an interface. Let's ask a question: what is an interface? Okay, so interface is just it's nothing but a boundary that separate 2 adjoining bulk phases. For example, let's say we have what is known as air-water interface. Okay, here air is one bulk phase and water is another bulk phase. The boundary that separates these 2 bulk phases is called interface. Okay, usually interface is constituted by 2 immiscible fluids. Example, liquid gas. Foam is a very good example for such application. Then we have liquid-liquid interface. For example, if you are placing any alkane, let's say oil on water, it is an immiscible mixture. So this water and oil being a liquid mixture, we call such system is also, such system also will, will exhibit interface, a boundary in between. And we have liquid solid interface. This example is, you can take an example of colloidal dispersion where you have solid and liquid boundary, and that essentially deals with liquid solid interfacial phenomena. So we have various liquid fluid interfacial aspects. So one can, depending on the application, one can understand further in detail. Usually the alkane and water system, let's for example any alkane, let's say you have hexane and water or decane and water. Usually the boundary, although we could see the boundary through naked eye, the thickness of the boundary, the interfacial zone, usually very, very small in dimension, usually nanometer level. Okay, it was using MD simulations also, people have predicted the thickness of the liquid-liquid interface boundary, which is usually between 1 nanometer, typically goes up to few nanometer. Okay, and to also motivate you further, you can take any other further. You can take an example of, let's say, instead of water oil interface system, if you take water interface, for example, let's say I take a polymer, two immiscible or two thermodynamically incompatible polymer, which means that I dissolve polymer type A in water and polymer type B in water, and if I mix them together, that also exists in two phase. Okay, so you will get two immiscible mixtures. Okay, interestingly, what is the thickness of this boundary when it comes to water and water emulsion? People have measured that it is a few tens of nanometer. Okay, so it's very interesting fact, right? For alkane water, it is very low, but for water in water system, it is quite high, right? And I want to throw some of the numbers so that you can relate quickly yourself. Say, for example, what is the interfacial tension of air-water system? Okay, it is 72 millinewton per meter. What if I replace air with carbon tetrachloride? Okay, in that case, the interfacial tension itself changes drastically. That is 45 millinewton per meter, right? So this is the change is due to the various intermolecular interactions between the different type of molecules here, right? So that essentially tells importance of the interfacial phenomena. Okay, so I have listed. So I have also highlighted here. You can also see here that what is the interfacial tension of, let's say, if I prepare two different polymer, water system, water in water emulsion, or two different polymer systems, let's say PUO in water and Dextran in water, they also phase separate. You can also treat them as any system like water oil and water alkane system. You see the interfacial tension of such system is 1 micronewton per meter, which is at least 3 to 4 orders lower than any alkane water system. Okay, so this essentially tells about the importance of interfacial system. One has to study why one has to study interfacial phenomena, right? So I listed several applications to motivate you. Probably you can go through this application, whatever I have listed here, right? Right. So here I would like to motivate you further by discussing about some of the naturally occurring interfacial phenomena which we often see, right, in our day-to-day life. The first one is capillary rise, right? If you can see that the water rises through the capillary column, the level of the water goes up, okay? And this is actually due to the surface tension, right, between the water and the surface, right? And this capillary effect is also seen in many natural system like plant or even in the tree, there the water which is collected at the root level is conducted from the root, and then it is distributed through the root and distributed to all the branches and leaves, is because of this capillary effect through the xylem tissue. The xylem tissue consists of a variety of water conducting cells. Each cell is acting like a capillary tube in itself, and those actually conduct water, and then it supplies all the water to up to the branches and leaves of the tree. Okay, this is very important phenomena. And after that, we look at the spider web. How spider builds its home is basically using the sticky threads that it generates through its gland. So nature offers them a gland which actually generates the sticky threads. Okay, and the beauty of this thread is, it actually manifests both intermolecular and intramolecular interaction. Okay, so between the junction, the sticky thread provides very good. There is a strong interaction between the thread among the thread itself. At the same time, this web is not just hanging in the air, right? It is also connected to the surface. So it also shares the intermolecular, strong intermolecular attraction between the thread and the surface, because of which the spider web exists. It's a good example of both inter as well as intramolecular interaction, right? The last one is the water strider. How insect walk on the water, right? It is because of what is known as the tiny hairs, that exists around its legs, right? And that repel water and capture air. Because it captures more air molecules in the as pockets, they actually generate net buoyant force, and because of which the insects can overcome the gravity, okay, and another force that acts downward, and due to that, the wasps can freely walk on the surface, right? So this is a good example of interfacial system, and there are several examples. One can give, the tears of wine is because of the Marangoni effect. Okay, the drop of water, when you stop the flow of water, there is a water drop that tends to it doesn't fall easily. It's because of the surface tension effect. Okay, once the droplet grows in size, once the gravity becomes dominant, it overcomes the surface tension force, then this droplet falls down. Okay, so this effect is surface tension effect. Okay, and the tears of wine, you would often wonder why it collects tears of wine, is because of the Marangoni effect. I have listed some of I provided some link here so that you can understand, several science experiments, okay, that involve surface tension and other interfacial phenomena. Okay, so we will stop here. We will continue from the next lecture. Thank you.